Hello everyone, welcome back to Dekin Cut. So we will finally be taking a look at the last problem of the IMO 2024, problem number 6. And of course, problem number 6 is never going to be an easy task, so without further ado, let us take a look at this problem. So problem 6 is a functional equation problem. So the problem statement is as follows. A function f from rational number to rational number is called Archimedean if the following property holds. For every xy rational number, either f of x plus fy equals fx plus y, or f of x plus y equals x plus fy. So this is a bit confusing, which I will try and unpack a little for you later. Show that there exists an integer c such that for any Archimedean function f, there are at most c different rational numbers of the form fr plus f minus r for some rational number r, and find the smallest possible value of c. So the last statement is also slightly confusing sounding, so let me unpack it a little for you as well. So what this means is that take a Archimedean function. I run through all possible values of rational number here, and each time I put in a rational number I get some value, right? So I look at all the rational numbers I can plug in. This gives me a whole bunch of different values as the output. I ask myself, how many distinct values did I get as a result of this for this particular Archimedean function? Maybe for one Archimedean function out there I get 10 distinct values. Maybe for another Archimedean function out there, I only get 3 distinct values. I need to find the best upper bound C that bounds the number of distinct values I can ever get from an Archimedean function. So if one Archimedean function out there gives me 10, another Archimedean function out there gives me only 3 distinct values, and there's no other Archimedean function in the world, then the best upper bound in my case would have been 10. Okay, of course, the numbers 10 and 3 were just made up. I just hypothetically came up with this. We will see what is the answer later on. Okay, how about these equations over here that describes a function as Archimedean? By the way, the word Archimedean is just a reference to Archimedes, which is the former name of Bath, UK when it was under the Romans. Yeah, of course, Bath, UK is the site of the IMO 2024. Yeah, just a little fun fact in case you are wondering where this name came from. Okay, so how about this property over here? Before going to that, I want to introduce a piece of notation that's going to be useful for us later on. So I'm going to write A maps to B if FA is equal to B. Yeah, so it's quite intuitive. Under F, A gets mapped to B. So with this notation, I can write, x gets mapped to fx and y gets mapped to fy. And what these equations are saying is either the yellow cross term is mapped to the blue cross term, or the blue cross term is mapped to the yellow cross term. You can check for yourself. The thing inside the bracket here is the yellow cross term, and outside here is the blue cross term. And similarly, the terms inside here is the blue cross term, and the terms here is the yellow cross term. So the reason this notation comes in useful is it will really help us simplify the equations we see later and not have to deal with so many f's that make our eyes like hurt so much. Yeah, so this is a pretty neat way, a pretty neat mnemonic, if you will, of describing this property. Okay, enough digestion of the problem. Let us now talk about the solution. So usually I will go through some motivation before presenting the solution. But in this case, I would say some of the first few steps are actually quite natural things that you will try for a functional equation question. So let us directly work through some of these steps. When you get a functional equation question, normally you would want to substitute in special values. So one special value in this case is x and y being the same thing. So if we put in x and y as both of them as x, then you get fx plus fx equals fx plus x like this. Or the other equation is exactly the same. Fx plus x equals x plus fx. So both of them give you the same equation. So thankfully, you don't have to choose either of these. It's the same thing. So this is one useful piece of information. The second useful piece of information is obviously you can set x equals to 0 and see what happens. So in this case, you get f of f0 equals f0. Okay, so you can continue substituting more values, but for now, these are the only two useful pieces of information that will come in handy later. So I'm going to park them to one side. This is going to be the list of all the useful facts that we have learned so far. Okay, one of the next things you might want to do for a functional equation question that is quite common is check whether the function is injective or not. And in this case, it turns out that f is indeed injective. And the way you prove the claim is, again, applying the standard trick you will do for functional equation questions. Namely, you suppose that fx equals fy, and you prove that this forces x equals to y. So how do we prove that x equals to y in this case? Well, now, you have two scenarios. So suppose fx equals fy and you put in the x and y. Either this equation is true or this equation is true. If the first equation is true, then what you have is fx plus y, which is the same thing here, and I just flipping the equation around. So this is equals to f of x plus fy. Yeah, it's just this part here. The nice thing is fy is the same as fx, so I can replace it with fx. And why do I bother doing this? Well, I have x plus fx. Hey, look at this property that we just discovered earlier. So f of that thing is fx plus x itself again. And now we have fx plus y equals fx plus x. So x equals y as we desired. And of course, if the other equation is true instead, we can run through a very similar manipulation and get x equals to y. So we conclude that f is injective. Let's note that down. Now, here's a fun fact. Once you know that f is injective, you can relook at this equation, f0 equals f0. So when f is injective, it means whenever f of a equals f of b, then a equals b, right? So in this case, the terms inside the bracket in yellow are going to be equal to each other. So in fact, f0 equals 0. Very good. We have strengthened this equation over here. So f0 equals 0. What's the next thing we want to do? Well, now that we know f0 equals 0, you naturally want to make use of this fact. So if you look around, you might want to see where can you create f0 out of something. So if we substitute y equals to minus fx, this will be 0. So it looks like it might be something useful to try out. So indeed, if we substitute y equals to minus fx, either the left equation or the right equation is true. So the left equation, I put y equals minus fx here. Unfortunately, this looks really complicated. But the right side is just 0, which looks nice. On the other equation, this will become 0. And this, I put y equals minus fx. So this becomes that complicated bit. So it might look a bit disheartening at first, but you need to apply your f0 equals 0 logic. Now, first, f something equals 0, f0 equals 0, and f is injective. So this something must be 0. So x plus f minus fx equals 0. So the first equation gives us this. You might say, oh no, I have to consider the second equation as well. What if the second equation is true? Well, thankfully, f0 equals 0. So you get x plus f minus fx equals 0. And that is exactly the same equation. So both equations lead to the same equation, which should set off alarm bells in your head to tell you that, wow, this is going along the right track. Okay, so what do we do with this equation? Well, you could move x to the other side and have minus x equals this, which doesn't seem that useful. The trick is if you replace x with minus x, make that substitution, then you get x equals to f of minus f minus x. You'll be thinking to yourself, Why do I make this substitution and make this right side so complicated with a whole bunch of minus? Well, the thing is, you have now just written x equals f of something. So every x can be written as f of something. This means that f is surjective. See, no matter what x you have, you can make it the target of something. So combining with f injective, we now get f is bijective, which is a very useful conclusion and something that you commonly want to track for a functional equation question. Very good. Now, the other thing that we want to take note of is that since x equals f of something, this something will then be the inverse of x. Okay, so f is bijective. I can now write f inverse. It's perfectly justified. And the f inverse of x is basically the something that's inside the bracket here. So let us write this down in case we need an expression for f inverse x in the future. Oh, but by the way, you should realize that this is going to be useful because look at this f minus r here and this f minus x here. This is where your f minus r is appearing. So you should be thinking to yourself that things are starting to look good over here. Okay, one more piece of information that we will want to write down, which is that if u is mapped to v, then you can apply a very nice trick that actually, therefore, minus v gets mapped to minus u. Where can I see this? I can see this from this equation. So the minus of fx gets mapped under f to minus x. You see, this fx here is basically the v. So the image of x over here, if I take the negative, it gets mapped to minus x. So this arrow is going to come in very handy in recording information. We have a sort of pictorial way of capturing some of these relationships. And here pictorially, u goes to v means at the same time minus v goes to minus u. Okay, enough about this. Let us now try to solve this equation, solve this problem. We haven't even used this fr plus f minus r anywhere. We have been dealing with properties of f so far. So right now what we have is we can actually write down a chain of mapping. We have minus f inverse x gets mapped to x, gets mapped to fx. This is just the definition of f inverse and f. And we, as I mentioned, we haven't really made this expression appear anywhere so far in our analysis. Well, the trick is you can always add and subtract a term to make such things appear. So you can add f minus x and subtract back f minus x. So this fx is the same as this. And you might be thinking to yourself, okay, I have created the fx plus f minus x over here. What's the big deal? The big deal is actually your other term here, minus f minus x, is exactly f inverse x. So you should realize that, oh, I'm starting to create something really interesting here. This is things you are caring about, and this is something that you have seen earlier in the chain. So, okay, I have managed to do something with my chain, but I still haven't really been starting to work on this problem. So, okay, fine. Let's start to actually look at this actual problem itself. So, you want to find out what happens, like what is the number of distinct possible values you can get for this expression as your r varies across all the rational number. So, having been thrown by problem 5, you might be thinking, okay, maybe you can't even have two distinct different values. Maybe everything must look the same. So the natural thing to consider is, let's say that you have two distinct values for the output. Okay, so let's say you have a x such that fx plus f minus x is a, and then fy plus f minus y is b, where a is not going to be. So you start with two distinct values of the image. What can we say about this situation? Okay, so we have the chain as we saw earlier. So for the X chain, you basically have this. We saw that we can put in the value here and you still have plus F inverse X. So this is the X chain from earlier. And then this is the corresponding Y chain. Okay, now let us apply the equation property. The thing is, let us focus on this mapping function and this mapping over here. So recall the mnemonic that we have earlier. When we have a pair of maps, and so if we substitute in F inverse X and Y into the equation, what we have is either the one cross term equals to the other cross gets mapped to the other cross term, or the other cross term gets mapped to the first cross term. So that's what I've written here. So one of the cross term is F inverse X plus B plus F inverse Y, which is this. This gets mapped to the other cross term, which is X plus Y. Or the other cross term X plus Y gets mapped to the first cross term. Yeah, so the mnemonic turns out really useful here to organize the information quickly without having to deal with all the substitution into here and mess your brain up. Okay, how about the other pair of mapping relationship here? If I do this again, I have one cross term mapped to the other cross term, or the other cross term mapped to the first cross term. So again, I write down the two sets of equation. So you might be thinking to yourself, why did I bother picking this pair of equations to look at and this pair of relationship to look at? It seems very random. The thing is, X plus Y is a common cross term to all these choices that I have made. So why is that useful? Now you can ask yourself, can we have this option with this option? No, because you have X plus Y on the right side for both of them, and F is injective. So you cannot have this thing and this thing mapping to X plus Y at the same time, because A is not equal to B. So this thing and this thing are both different from each other. Similarly, can you have this and this holding at the same time? No, because X plus Y must map to only one possible value, and A and B are distinct, so you cannot have both holding at the same time. Okay, so this is probably some back justification to show you why what I just did is useful. And well, now we know that either this chain of relationship holds, which is very nice again, this maps to X plus Y, which maps to this. Or you have this maps to X plus Y, which maps to this. Right? So the two scenarios connect to each other, which is very nice. So one of the scenarios is this, as I mentioned, or we have the other case. So I'm just going to consider this case, and the other case will be completely analogous. I'll explain at the end what happens if you consider the other case. So let's focus on this case. So we have yet another chain over here. And I promise you, we'll only need one more chain and then we'll be done. So the last chain that we need is flipping this relationship backwards using this property. Okay, so Y gets mapped to B plus F inverse Y. So I have negative of this maps to negative of Y. So I just wrote this down here. And why did I bother writing this extra chain down? That's because I am now going to consider these two relationships. And something nice will come out again when you plug in the X plus Y and minus B minus F inverse Y into the equation property. So by this stage, you must be really thankful that I'm using the mnemonic, because if I plug this thing into the equations, I tell you, everyone's head is going to explode. So thankfully, I'm going to use the mnemonic. So if I take one cross term, oh, very nice. This is just x, the y minus y cancel out. The other cross term is going to have the minus f inverse y cancel the f inverse y here. So this is partly why I'm taking the flip version of this, so that when I do this step that I'm doing now, many of the terms cancel. So again, a bit of back justification. But in any case, right now I have one cross term mapped to the other cross term, or the other cross term mapped to the first cross term. So this is absolutely perfect now, because you might be thinking to yourself, oh no, I have two cases to consider again. But actually, one of these cases cannot even happen, because we see over here, we already know that it must be f inverse x that is mapping to x, and f is injective. So can you have this mapping to x as well? No, because a is not equals to b. So this thing is not f inverse x, so it cannot map to x. So this case is out. And now we are left with this case. X maps to this, but we know that x maps to a plus f inverse x, a plus f inverse x. So it must be that b is therefore 0. Now, take a moment and fathom what we have just discovered. We have just discovered that whenever we have two different output in the image of this, one of them must be 0. Over here, I showed that b is 0, but remember earlier, we had two cases and I only considered one of the case. The other case turns out will tell us that a equals 0. So it will either be b equals 0 or a equals 0. So the upshot is that whenever you have a not equals to b, one of them must be 0. And this is a huge discovery, because it basically means that you can only have at most two distinct values for this expression. Because if you have two non-zero distinct values, then you put in those as a and b, and then you get the contradiction that one of them must be 0. Yeah, so this tells us that there can only be two distinct values, and in fact, one of them is 0, the other one is a non-zero number. Okay, so the answer so far is C is going to be at most 2. But can you get two distinct values? Maybe it turns out that there can only be one distinct value. Or maybe there isn't even any equation function. That would be a massive throw. But it turns out that yes, you can use fx equals to floor of x minus the fractional part of x. And I'll leave you to check that f is equation. It is not so trivial that you can eyeball this, but it is also not difficult. It's just a bunch of straightforward algebra. And I will leave you to check that fr plus f minus r is either 0 if r is integer, or minus 2 if r is not integer. So indeed, you can get two distinct values. So that is all for problem 6. What do you think of this problem and this year's IMO? I'm glad to be able to cover all the problems relatively quickly, and I hope you enjoyed this series of videos as well. Do stay tuned to the channel for more Math Olympiad videos, and I hope to see you in the next video.